we're going to use Descartes' rule of signs to determine the number of positive roots of equation and the number of negative roots of equation and number of imaginary roots of equation without actually solving for the roots. So for example, if we have degree 3 equation, and we know it's hard to solve an equation with higher order than 2. So here we don't really need to, our goal is not to solve the equation, we just try to determine how many positive roots, negative, or imaginary roots. But using Descartes' rule of signs, first of all, we know Descartes had proved that every equation, so the first rule number 1, every equation can have as many distinct roots as the number of dimensions of the unknown quantity in the equation. So pretty much means, for example, if you look at the highest power, the degree of this equation is 3. So that means we're going to have 3 roots in total, which includes positive, negative, and imaginary. So we can write down the number of roots is equal to the highest power of x, the variable, or you can call it a degree. So in this case, we know that this equation, by rule number 1, we know this equation has 3 roots. Now we're going to determine out of these 3 roots, how many are positive, how many are not negative, and how many are imaginary. So here we're going to look at rule number 2, which says the consecutive terms present a variation in signs if the coefficients have opposite signs. So for example, in this case, we look at 2 consecutive terms, look at these 2, and take a look at the coefficients. They're both positive, 1 and 1. The number 1s are omitted, so there's no sign change here. But if we look at the second term, the third term, the coefficient of x squared is positive 1, but the coefficient of x is negative 1, so there is a sign change. And if we look at the third term and the fourth term, the coefficient of x is negative 1, but the constant term has a positive 2. So from negative to positive, that's a sign change, and because they have opposite signs. And so Descartes' second rule says the number of positive roots is equal to the number of sign changes, or you can say the variations in the signs of the coefficients. So I'll just put the number of sign changes, or to this number decreased by a positive even integer. What it means is we can look at this example right here. So we notice that there are 2 sign changes. 2 sign changes. The second between the first sign changes first term and second term. The second sign changes second term and third term. So there are 2 sign changes. So this is the number here, 2. And so the number of possible roots could be, there are different possibilities. It could be just, so we can say there are 2 positive roots. That's just one of the possibilities. Or 0 positive roots. How did I get number 0? By the rule, it says either the number of sign changes or this number decreased by a positive integer. So 2, we're going to decrease number 2 by a positive integer. So the first positive integer is going to be 2. So I do 2 minus 2, which gives me 0. Well, the second positive integer will be 4. So if I decrease 2 by 4, I get negative 2, which is impossible because the number of roots won't be negative. And so there are only 2 possibilities. But if there are, for example, say 5 sign changes, and if there are 5 sign changes, and then when you decrease it by 2, then you can get 3, and you decrease by 2, you can get 1, and you cannot decrease it any further because you can get negative. So then this equation will have 5 positive roots, or 3 positive roots, or 1 positive root. So that's what it means. And now we can look at next number of negative roots. When we determine the number of negative roots, we're going to do a little bit of change here. We're going to replace the letter x, the variable x in the original equation with the negative x. So for example, when we see a letter x here, we're going to put a negative x there and copy everything else, and x squared, we replace it with negative x, and copy minus, and when we see the letter x, we replace it with negative x. Notice we have 2 minus sign here. One comes from original equation, the other is the negative sign we added. The reason we're doing this is because when we replace every x with a negative x, and that's the opposite of x. If x is positive, then negative x will be negative. So if x is negative, then negative x will be positive. So that means if you want to look at the negative roots of the original equation, which corresponds to a positive root in the new equation we get. So, and we know how to determine the number of positive roots by rule number 2. So let's reduce this a little bit. And negative x cubed, by algebra we know that it's going to be negative x cubed. Negative x squared will be positive x squared, and negative times negative will be positive x, and plus 2 equals 0. So let's see how many positive roots does this new equation have. That would be the number of negative roots, because each positive root of this new equation corresponds to a negative root of the old equation. So let's check how many sign changes. We have from negative 1 to positive 1, that's a sign change. Positive to positive, no sign change. Positive to positive, no sign change. So there's only 1 sign change. By rule number 2, this tells us this new equation has only 1 positive root, or decrease by 2. If we decrease 1 by 2, we get negative. That's not possible. So 1 positive root, which means the original equation, has 1 negative root. Okay, so we found out that this equation possibly has 3 roots. Well, it definitely has 3 roots, and we know that it definitely has 1 negative root, and the other 2 either 2 positive roots or 2 imaginary, because if it does not have 2 positive roots, if it has 0 positive roots, that means that the other 2 has to be imaginary. So